we are only asked to find the forces in CD, CF, FG, and DE. So we want 4 of the total of the 10 or so members that make up this truss. So right away, this is an indication that we probably want to make at least one section cut in our solution process. And we're given just the diagram. With this in mind, that we're only interested in the forces in these 4 members, what would be a good, well, actually taking a step back, we first want to analyze our entire system, and we want to see is it statically determinate or statically indeterminate. Now, looking at our system and how it's supported by the ground, is it statically determinate or indeterminate? We have a rocker at E, and we have a pin at A. So we have 3 reaction forces, meaning that this is statically determinate. So what's the first thing we should do in starting to solve this problem? Yeah. Right. Starting, we can find our supports, our 3 reactions. We do want to draw the external free body diagram to find AX, AY, and EY. At A, I have that AY and AX. I have 2 applied loads of 6 and 8 kilonewtons. And then at E, I have just that normal force, or just that upward force, EY. And that's 3 and 3 and 3. And those are the only forces acting on this, so I can use this to write my equilibrium equations in order to find these external or these support reactions. I'll start with the x direction. I just have AX. So that makes things simple. AX must be 0. And then I'll have AY and EY left to find. If I take a moment equation around A, that's going to leave me only one unknown in my equation, EY. So I can find EY right away. That'll be negative 3 times 6 minus 6 times 8 plus 9 EY. So the value of EY, you should get, rounded a little bit, 7.3 kilonewtons, and that is up. And for the roller, it can, or the rocker, it can only be up because it's really only supplying a normal force. So finally, if we look in the y direction, we'll have our AY, we have our EY, minus 6 minus 8. So our last remaining unknown from this free body diagram, AY, we're going to get, again, positive 6.7 kilonewtons. Also up. Right, so again, before we even decide, do we want to make a section cut, do we want to make a pin diagram, we want to look at our system and see, is it statically indeterminate or statically determinate? If it's statically determinate, we're almost always better off by making this external free body diagram and then solving for those reactions. Almost always, I would say, do not cut through more than 3 members and try to cut through as many members that you ultimately want as possible. We're interested in 4. We can't make a cut that goes through all 4, but we could make a first cut that goes through as many as possible. Since we want CD, we want CF, and we want FG, and we want DE, I can at least make a cut that goes through 3 of the 4 members that I'm trying to find. So at least as a first step, again, as a clue here, because we're only interested in not every member, but 4 of them, probably making a section cut first is a good first internal free body diagram to make. Then we can decide after that what our next, do we want to make a pin diagram, another section, or so on. So I make my second free body diagram, now making that internal cut. Everything on this side that I'm not cutting through, I'm just going to copy exactly. So remember, FD, DE, FE, completely unaffected by this cut. So that just gets copied. And I also copy any of the forces that affect those joints that are still intact here. So at point F, I will be including that applied force of 8 kilonewtons down. And at point E, I have the rocker with a value of EY. And in this case, I will put the actual number for this picture. That was 7.3. Now for the three members that I cut through, I can now see the force CD, which is to the left. I can see the force FG. And I can now see the force CF. And because these are equilateral triangles that make up this truss, I know that the force CF is at a 60-degree angle from the horizontal. This length I want to put in is going to be 3 meters. And I'm going to want to know this vertical height because this force CD, or when I'm taking a moment equation, that distance is going to be important. So the vertical height I have to figure out, which I can do using the fact that it's a 60-degree triangle. I know that the height is going to be, using the 60 degrees here, if the hypotenuse is 3, then I can use the sine, or 3 times the sine of 60, to figure out what this distance is here, the height of the triangle. So I can either do that as a decimal, or I did it with exact values, because sine of 60 is going to be root 3 over 2. So this height is root 3 over 2. For the fourth equation, looking at this, they all have x components. Only CF has a y component, though. So summing forces y is a pretty good place to start for figure 2. So in the y direction, I have FCF sine 60. And I have the 8 down and the 7.3 up. So from here, solving for FCF, moving the 8 over, the 7.3 over, it is positive. I get about 0.81. So that will be in tension. Next, I can, again, they all have x components, but since 2 of them emanate from point F, if I take the moments around point F, I'll be able to eliminate 2 of those unknowns, and again, be left with only 1. The 8 acts at F, these 2 forces act at F, so the moments around F will actually only have 2 things that I need to consider. FCD times its distance, its perpendicular distance to point F, which will be this height. That'll be the 3 root 3 over 2, or its decimal equivalent. And the 7.3 times its distance of 3 meters. The CD is causing a counterclockwise, so it's positive, and the 7.3 also counterclockwise, so positive. So for CD, I'm getting a negative 8.43 kilonewtons, so compression. The x forces is where we have to be careful that we're writing the equation based on the picture with a negative FCD, a negative FFG, and a negative FCF cosine 60. Now here again, based on the picture, these are all negative. They all point to the left. But it did turn out that my CD value was negative or in compression. So when I put it into here, it'll be a negative times negative 8.43. So this will actually become a positive 8.43. So the keeping track of the sign on things is the tricky part here, and that's why always write it first as the variable, then put in its value later. So if we put that in and we put in our value for CF, then the last thing we don't know is FG. And we can solve for FG, and that's where I get a positive 8.03. And that should then be in tension. So again, we have a choice to make. We can now proceed. We definitely need another free body diagram, but we have our choice of what to make. What would be some options for the next free body diagram we could draw? So for the third free body diagram, just so we're all on the same page, draw the pin at D and the forces that affect it. We have the three members attached to it, FCD, FDE, that's 60 degrees below the horizontal, and FDF, also 60 below the horizontal. And CD we know from the previous step, so we're left with two things we don't know. I will say in retrospect, D was not a great choice that I made in my notes to do. E would have been easier, as we'll see from the equations that we derive from here. But we're trying to be as efficient as we can, but we don't want to spend a ton of time making the decision of what to cut and then run out of time to actually do the solution. So once you have enough practice, you'll get to see some of the better ideas than others. But even here, when I was doing it this afternoon, I just chose D, but E would have been better, or that section cut through ED, EF would have been mathematically a little bit easier. So based on the choice that I made, we're looking at D. Both DE and DF have X components and Y components, and that's what makes this just a little bit not as good a choice as if we chose the pin at E. Well, if we look in the X direction, we'll have negative FCD, which we know its value was the negative 8.43, minus FDF, cosine 60, plus FDE, cosine 60. So we are still left with these two unknowns in this equation, so we do need the eighth equation to solve for everything. And we'll be left with negative FDE sine 60 minus what is the other one? DF sine 60. And here at least the sine 60s do cancel. So we do know that FDE equals negative FDF. But we do need 7 and 8 simultaneously in order to solve for the two unknown, the values of DE and DF. So if we use 7 and 8, we can find along the way, even though we weren't asked to find it, that DF is going to be 8.43 in tension. But more importantly, what we need to know is DE is negative 8.43. So that one is actually in compression.